hand, whichever is simpler. Okay, yeah, fine. So today's lesson will be on data preprocessing and cleaning. That's a very important step in any data analytics or data science project that you may embark on. So the primary objective of data preprocessing and data cleaning, number one, is to transform the raw data into a format that you can easily feed into our machine learning models such that it can give us the predictions of the outputs that we need. That is if you're working on a predictive project or something like of that sort. Objective number two usually is to obtain any hidden insights that may be present in our data, but not visible at first glance. So sometimes you may find that you are supposed to dig into your data to come up with insights that may be hidden. In some cases, such insights may be very, very important in terms of guiding our actions and decisions based on the data and the problem that you're trying to solve. So today's session will be based on 4 libraries. That's pandas, numpy, matplotlib, and seaborn. So the first two, pandas and numpy, will be used for data wrangling and mathematical manipulation. And matplotlib and seaborn will be used basically for visualization. So this is going to be a practical session as usual, and allow me to share my screen. Okay, so I hope you guys are able to see my Jupyter Notebook screen over here. I'm just going to zoom in for those who had problems last time. So you guys are able to see clearly, right? Getting any response? Are you able to see my screen?
Yes.
Okay, fine.
Yes.
Thank you for the response. So I'm just going to outline here our objectives today. Our objectives. The performing processing of data. So cleaning and preprocessing data takes a lot of forms and techniques depending on the problem that you're trying to solve. So, however, we have some basic, what can I call them? Basic steps that have to be followed in almost every other project. So some of these steps include, I'm going to outline them here. Number one, you may want to check out for missing data, of course, and then you can either drop, or let's just say you can then handle the missing data if any. And then number two, we may want to look at any outliers. So we may check for outliers. Then number three, we may want to scale our data. We may also have categorical data that may need to be handled. And then finally, we may have to check the correlation of variables in the data. So essentially these 4 steps, or these 5 steps are there, no, 4 actually. I'm going to look at 4 steps: checking for outliers, scaling the data, handling categorical variables, and handling correlation among our variables. This first step here and other preprocessing tools, which I may miss out, will be handled tomorrow by my colleague, Mr. Kimani. Okay. So to do this, I'm going to use a data set that is called Boston housing data. This is a very common data set in almost every machine learning project. So essentially what this data set contains, so let me just show you here the resources using Python libraries. Yes. NumPy, matplotlib, and seaborn. Data. So this data was collected from a census conducted in Boston. Boston is in the United States, around in the 20th century. that evaluated the relationship between house prices or median house prices and different characteristics such as the crime rate in an area, the industrial zone, and things like those. So first I'm going to import all the libraries that I'm going to use, and then show you how the data looks like. I've already shared this notebook with Mr. Eric. So after this session, it's going to share it with you. So no need to worry. So as I said, pandas is for restructuring our data, numpy is for mathematical manipulation, and then these last two here are for data visualization. I'm going to load in my DF. So these are the columns. You have like crime zone, industrialization, all those. And then finally, our target variable, which will not be of any importance or any significant importance in this discussion, is the median value. It's in thousands. So like this represents 24,000 as the price of our house. So these are the values that we have over here. So of course, before you start doing anything with your data, you first have to get an overview of the general statistical distribution or statistical characteristics and overall shape of the data. So just do describe first for that. You can see that we have 486 entries, and for each of these entries, we have the mean of each column, standard deviation, minimum, lower quartile, median, upper quartile, and the maximum value. We can also do some basic info, can print out some basic information from our data set. You can see that we have 486 non-null values in some columns, while in others we have 506 non-null values. So essentially this means that our data is not clean. We can already see that we have missing data that may have to be addressed. However, as I said, that's not my topic for today. That will be handled tomorrow. So I'll go straight away to my first objective, which is outlier detection and handling. So if you look at this data, the way it is, we have like how many columns? I can do a basic shape here. We have 506 observations with 14 columns, 13 of which are independent variables and one is a dependent variable. So given this size of this data, it's very difficult to just say, based on first glance, if we have any outliers or things like those. So we may need to use different techniques to identify outliers in our data. 506 observations are quite few. So this is a relatively small data set, and one way which you can identify outliers in such a small data set is by leveraging on Seaborn's pair plot function. So what that does, it allows you to plot a pair plot of all these functions, like, of all these variables. So a pair plot basically will be plotting crime against zone, crime against industrialization, up to this last variable here, crime against median value, and then we'll repeat the same for each and every column here. So needless to say, if you have a very large data set, that's going to take a lot of computing resources, and you may need to explore other options of identifying outliers. So let me show you how you can come up with a pair plot quickly. So yeah, that's basically it. SNS.pair plot, and then you pass in your DF. Maybe we won't run that. It's going to take some time, maybe 30 seconds to 1 minute. So should be patient, and as it runs, just in case if anyone has any question, you can feel free to ask now. Okay, fine. I want to assume no one has a question at this point. Okay, so this is what a pair plot does. Essentially, it plots each column against the other in the entire data frame. So it gives you a general overview of your data and how it's distributed. For instance, you can see that we have some columns which are quite skewed in terms of the distribution of data. For instance, look at this column over here. We have a heavy tail towards your right, and interestingly, we can see that a plot of the median value seems to be normally distributed. So we can already conclude that our median value follows a Gaussian distribution, and therefore it's a target variable anyway. It doesn't need any much preprocessing. On the other hand, we have other columns here. For instance, there's age somewhere. We have other columns. If you look at this one here, it's much skewed towards the zero value. Let's see. You can also see that we have lots of outliers in columns such as this here, this one, this. Basically, the entire data set, most columns have outliers. So essentially, outliers are instances or observations in our particular columns which are found, or we can say that which are geometrically far away from most of the other columns. Like you can say that if you take, like, we pick this one here, able to see my cursor, you can say that these three observations here are outliers because they are located further away from most of the data set, most of the data points here. So this occurrence is undesirable because if you are fitting a machine learning model, for instance, these outliers are going to skew your results, and the overall accuracy or performance of your model may not be appropriate. So there are various ways in which you can remove your outliers. One way is to perform scaling of your data. Basically, what scaling does, scaling will ensure that if you have data between 0 to 100, it's going to convert them to a value between 0 and 1. So instead of having the initial scale comprising of large numbers and small numbers, you're going to have all your data within a scale of 0 to 1, such that the distance between those numbers will be very small. Okay, so instead of having this relationship, we'll have most of our variables clustered together. That's a very good term to use, but I hope you get the point. So scaling is one way of removing outliers. Another way is normalization. Normalization is in the case where we have data like in this histogram plot here. You can see that it's skewed towards the zero value, but if you normalize it, it's going to take a Gaussian or a bell-shaped distribution. So in this approach, we'll have tried and reduced outliers in our data. We'll not have eradicated them completely, but we'll have reduced them. Then the last technique is to actually drop all the outliers in our data. So for instance, I can decide to pass a filter function that says that for a given target column, if you're looking at age, for instance, the age of people, which is not in this data, just for explanation purposes, if I'm given data that has the age of people and I do my exploratory data analysis and I find that we have people with like 200 years, 300, we know that that is not realistic, at least not in the present age. So I may decide to pass a function that will drop all people with ages greater than 100, so that I'm only left with people whose age is reasonable. So all people with ages or years greater than 100, I'll have to drop them. If we have those with an age below 0, I'll also have to drop them because it doesn't make sense to be negative something years old. However, if you are working with a relatively small data set, you may not want to drop your data because the more data you drop, the more information you lose. So it's much better to apply techniques such as standardization, scaling, normalization, and things like those to try and fix your outliers. So I'm going to show you how to fix outliers using both scaling, normalization, and dropping columns. So Before I go on, is there anyone with a question on distribution of data in terms of Gaussian distribution and such? I hope you all understand Gaussian distribution of data. Okay, fine. If there's no question about that, I'll first show you a simple distribution of Gaussian distribution and log normalized data so that you may get an intuition or a basic intuition of how scaling and normalization works. So I'm going to create some random data. And first I'll begin by defining the size of the data. So I want my data points to be like 10,000 dimensions. Then I'm going to pass in my random seed for reproducibility. So my Gaussian data, this way. This is the function for creating randomly distributed data using NumPy. So it's NumPy np.random.normal, and then you pass in the size of your data. For my case, it will be n. And if I want skewed data, it's going to be numpy.random.log, sorry, log normal, for the same size. So now, if I plot for you the Gaussian data, sorry, so this is our normally distributed data. You can see that it's centered around 0. Yeah, and basically we have a standard deviation of 1. Now, if we plot data, we see that it has a heavy tail, okay, and definitely have outliers out here, okay. So now that we have this understanding, I want to show you how normalization to remove outliers. So we can say that normalized data is equals to, we'll use the log function. Log function is, or log transforms are one of the techniques that can be used to normalize our data and therefore remove outliers. So to implement it, you simply use the inbuilt NumPy log function, np.log, and then you pass in our skew data as the argument. Now, if you plot it, and then if you say our title, now you see that initially this is what we had, and then after applying the log function, this is what we obtained. Now, you need to be careful when using the log function, because it's not every time that the log function is going to return a normal distribution. It will try as much as possible to return this distribution, but there is no guarantee that it's going to work all the time. Then secondly, log transform does not apply in every case, okay? Sometimes you may transform your data and end up with all zeros, for instance. Or you may even get some infinity value. So instead of cleaning your data, you may end up actually adding more noise to your data. So because of that, I've attached some links to the notebook that I've shared with Mr. Eric that have further reading materials on how you can use the log function. Please take your time and go through the links. It may be helpful in your future endeavors. So now that we have a basic intuition of how the log function works and how it can be used to transform skewed data, we are going to select a random variable from our data frame and then transform it using the log transform. So the data frame that I selected for this purpose was, just confirm here, was the ls start. So let me print out. So I'm going to work with this column here. So initially, or the original column, this is how the original column is distributed. Very strong. So yeah, you can see most of our values are between the values of 0 and say 30. Beyond 30, we have some minor values here which we may consider as outliers. I'm not saying they are outliers, but the definition is quite relative. So in my case, I'll consider everything above 30 as outliers. So one way which I may try to address this is by normalizing this data. So you can see that normalized the start, the np.log. So now, if I visualize this thing, so it looks like. So if you look keenly, you'll see that we had a scale of 0 to 40 initially, but now we have a scale of 0 to 4 because we are working the log transform. Then these outliers here have been significantly reduced. Okay, so yes, that's one way of removing outliers. The second way that I'd promised to show you, we may actually just drop outliers. So in our case, let's drop everything that is greater than 30. So, and for that, you can say that you can create a new variable, maybe a new data frame called df without outliers. You can say that fixing the argument lstart, and all values of lstart should be less than or equal to 30. Okay. Now, if I plot the same again, you'll see now that beyond 30, we don't have any other outlier. So basically, these are the two ways that I wanted to show you about removing outliers, but there are other ways which have shared links in the notebook that will be shared with you. You can refer to them later on. At this point, do you have any other questions so far? If I move on to the next thing.
Excuse me, sir.
Yes.
Is there any other formula for doing the normalization? Or
Yes.
you have to.
You're saying something.
Or you have to use the log libraries available by the Python.
No, I've just shown you the one way. One way of doing normalization is using the log approach. There are also other transforms as well. In Python, there is a library called sklearn, which comes with a preprocessing tool that contains different transforms. We have the power transform, the log transform, and under the power transform, we have transforms like Box-Cox transformation, and then we have another one called the Yeo-Johnson transformation. The links to those are provided in the notebook that will be shared to you. So I think that will address your problem.
Okay, thank you.
Welcome. Is there anyone else with a question?
Yes, excuse me, I have a question.
Yeah.
You lost me when we were talking about this, like, now, would you mind scrolling down a little bit?
Here?
Yeah, the outliers. Would you care to define what are the outliers that you said drop outliers? I haven't come across them through the notes.
Okay. Let me demonstrate one outlier, for instance. I think I'm going to just a moment.
Okay, as Mariam is coming on, I mean, the word outlier, mostly you find it being used in machine learning or data science, but in a layman's language, an outlier is maybe a record that is far away from the range of other records. And I think Marim used an example that you see, you will understand that most of the undergraduate students will range between age 18 to 24 there, let's say, for example. But there are occasions when you will find there is an undergraduate student who has got 40 years. So the student who is now spread to 40 years is an outlier. Then the implication is that if you don't normalize, whatever model or whatever problem that you want to solve, the student will be factored in, and you will find that the performance of that model, the accuracy will not be okay because you've got few points that are spread very far away. I think that is what I wanted to explain as Mwalimu is plotting that.
Okay, thank you for that explanation. Just to make it more clearer. So if you look at this, scatter plot here, not communicating the message they wanted, but it will still serve the purpose. We have a relationship between house price and crime. So we are expecting, we are expecting that in places where the crime rates are high, if 80 represents high crime rate, you are expecting that in cases where crime rate is high, the prices of the house will drop. And in cases where crime rate is low, house price should rise. That is generally what is expected in any society. In this case, however, we have cases where the crime rate is low, 0, and the house price is very high, 50. And we still have the same situation where we have like a very high crime rate with a similar house price as a place where the crime rate is low. So we can consider these extreme instances here, maybe say from 40 onwards on the x-axis as outliers, because they don't conform to the general pattern which we expected to see. This representation may not be quite clear, but it serves the purpose of showing you what an outlier is. An outlier is basically a data observation that is located far from the median or the mean of the actual observation that you are interested in. Yes, Margaret. Okay, fine. Is there anyone else with another question? First of all, I hope that I've answered your question, whoever had asked about outliers. Yes, Margaret. Margaret, would you like to say something? Okay. I assume you don't. So can I proceed?
As we go on, I encourage that people have a pen and a paper where you can put some notes down, because a lot is spoken and so much is done. So when you have got a pen and a paper, then you are able to follow up nicely. Thank you.
Okay, guys. So if there's no one with a question or a concern, I'm going to move on to the next thing that I wanted to share with you this evening, which is scaling the data. So already we've spoken about data normalization, and you've seen that the objective of normalizing our data is to try and achieve a Gaussian-like distribution. You'll find that in most algorithms which you may end up using in your projects, they are unable to handle data that is skewed. However, we have other algorithms which have inbuilt capabilities of understanding that your data is skewed, and therefore they may have to normalize it. But that's not, in most cases, it's not advisable to rely on such algorithms. So that's why scaling your data may be necessary depending on the kind of problem that you're trying to solve. I mean, normalizing your data, not scaling. The purpose of scaling, as I had said, is to convert your data into a reasonable scale. For instance, if I have a scale of 0 to 100, we have some values maybe with 5 and others with 95. We may see that the difference between these two might be extreme, and then that may affect things like the mean, standard deviation, and things like those. So we want to convert this large scale into a relatively smaller scale between 0 and 1, which we may work with easily. So I'm going to show you how that can be done with NumPy, although Python has inbuilt functionalities again, which can be used to solve this problem. We have like the min-max scalar and the standard scalar, but in most cases, the min-max scalar is the one that's used to transform the scale from, say, 0 to 100 to 0 and 1. So enough talking. Let me show you here scaling. I'll start with the basic formula. So this is how it's performed. You take the difference between the observed instance and the minimum of that instance, and then we'll divide it by the difference between the maximum of that particular variable. So I'm going to pass in x max here minus the minimum of the variable. Okay. So to obtain our x scaled, we'll take x minus the minimum of x divided by the maximum of x over the minimum of x for every column. Okay. So for purposes of demonstration, I'm going to work with a column called zone. So let's say that zone. That. So just to show you first, I want to show you the minimum and the maximum values of this column. You can see that we have a minimum of 0 and a maximum of 100. In some cases, this may be extreme. Maybe it's negative x and positive y. So it's quite a large scale that we may want to scale. So to implement the min-max scalar using NumPy, I'm going to define a function, call it min-max scalar. For those of you who are not yet familiar with Python functions, I'll advise that you take a brief tour on the same, because they'll turn out to be very helpful when you're working on your projects. So what this function does is that it's going to return this formula over here. So I'm going to say scale result to be a column here minus numpy.min that column divided by the maximum of that column, the difference between the maximum of the column and the minimum. Then this function will just return the result. Okay, now I want to find the scaled zone. So I'm just going to say that the scale zone will be the min-max scalar, and the argument that will be taken will be this zone that I defined here earlier. So now we expect that if we explore the maximum and the minimum of this, it's going to return 0 and 1. So we have the minimum is 0 and the maximum is 1. Up to that point, do you have anyone with a question? No, it cannot be removed through the mean and the median. Instead, we can do this through transformation, such as normalization and scaling. That's for Margaret. For Norbert, what are the other ways of plotting graphs? I don't have a clear answer for this. You could check out Matplotlib, Seaborn. There is also Plotly. Yeah, those are the most commonly used visualizations for Python. However, there's another unique visualization tool called AutoVis that will plot like generally every relationship in your data using only two commands of one, two commands. But before you get to that point, let's first grasp the basics. Someone had raised their hand. Is there any other question? The code below scaling. Which one? This one here. No, but could you please speak? This one. Okay. Markdown supports formulas. You can write formulas on Markdown in LaTeX command. So you may want to check out LaTeX first. Let me just show you here in the chat section. Check that out. So it's a tool that's commonly used to write scientific articles and mathematical articles. So it's the same technique that has been used to write the formula over here. Any other question? Okay, so I'm going to assume there's none, and then I'll proceed. So the next thing that I wanted to discuss with you guys this evening is handling categorical data. So what is categorical data? Occasionally, let me print this out. This is how most of your data frames will be looking like. And you can see that we have columns that have continuous variables and others that may not necessarily be having continuous variables. So categorical data is basically data that can be classified into one of many categories. Say if you had a column here of gender, for instance, we know that we have like two widely known genders, male and female. We can have data that is looking at things like your level of study and maybe your location, your year of birth, or maybe let's say we have data that is collected between 2 years, 2020 and 2021. We can consider 2020 and 2020, I mean, the column year as categorical because the data can either belong to 2020 or 2021. Categorical data may be very important in your models because in some cases, they may actually be key determinants in the output of the predictor variables. So knowing how to handle them is very important. Another thing that I would like to mention is that your categorical data may be either in numeric format, as seen in the year, or even age, or it may be in text format, as seen in the gender example, maybe male or female, things like those. So depending on the format, you may want to come up with different ways of handling them. So I'm going to show you two basic ways of handling categorical data. The first one is called get dummies function. So essentially what it does, the get dummies for every category in your column, it is going to create another column that will be encoded. So if you, okay, let me just demonstrate that practically because explaining it might be a little bit confusing. So first, allow me to do this. So I identify these charts as categorical because look, we only have two values, 0 and 1. So one way of knowing that your data is categorical is when, sorry, I've just lost my electricity. Okay, as I was saying, one way of knowing that your data is categorical is when, if you print out the unique function, you'll find that you have maybe 2, 3, 4, let's just say a small number of unique values in that specific column. Initially, our data frame has like, let's try and print it out here. Our data has 394 observations, and for this particular column, all these observations are either 0 or 1. So that means that our data is categorical. So how do you handle it? So one way of handling categorical data is by using the dummies function, as I'd say. Just give me a moment. So you can use the pandas get dummies function. You can say that create a new data frame that will contain this column which has been encoded. Call it encoded df. For that, first let's point out that our categorical column is called chars, and then encoded df we obtain this way. So the pd.get dummies function takes in a few arguments. The first argument will be the data that is going to be encoded. So for our case, the data will be our new df here, this one. And then the categorical columns for which you need to create these dummies. So the columns will be the cat calls that we just defined. once we've done that, we can print out the first two rows of our data frame. Call, not cut call, sorry for that. Sorry. Okay, so now if you look initially, initially, this is how we had our data. We had these charts over here, and our data ended with the median value. But after using this .getDummies functionality, we ended up with two new columns. We have the chars 0.0 and chars 1.0. So essentially what the .getDummies does is that for every categorical column, depending on the number of unique features in your column, it's going to create an equal number of new columns in your new data frame, with each column representing each categorical feature here. So for instance, if we had like we saw that we had 0 and 1 as our unique values, so it has created column 1 for zeros and encoded these columns with 1. And it also created a new column here, chars 1.0. And since our first one here was 0.00, it's going to assign 1. It's going to assign 1 here and 0 for chars 1.0, implying that we're going to treat this as a null. Okay, you should be careful, not as a missing value, but as a null value. So that is how .getDummies operates. So of course, based on this simple example here, it goes without saying that if you have multiple categorical features in your data, then you're going to end up with a lot of columns here, and that may bring some dimensionality problems when you're working with extremely large data sets. Of course, we may also need to consider the computational resources that will be consumed. We don't want to end up with a column with, say, 580 columns. I mean, a data frame with 580 columns. It doesn't make sense to do that. So that's why we have other methods of handling categorical data. These include or improving the performance of your machine learning model. So that's what I'm going to implement next. But before I proceed, do you have any other question?
Excuse me, sir.
Yes.
No, can you just clarify on the getDummies function? Does it imply that it only works with the columns with the two unique values, or what if maybe the column has got 3? Will getDummies affect
Yes.
such columns?
It will still work depending on the number of unique values in your specific columns or in your specific column. The .getDummies function is going to create an equal number of columns. So if in this column chars maybe I had 4 unique values, it's going to create 4 new columns in my data frame. Typically chars 0, 0, chars 1, chars 2, chars 3, chars 4. So the number of unique values in your column doesn't really affect the output. Does that answer your question?
Okay, thank you.
Welcome. Any other question? Okay, fine. If there's no question, I'm going to quickly show you how you can implement the frequency encoding technique. It's quite custom, and I think that's one of the reasons why it tends to improve the performance of machine learning models. So implementing frequency encoding. Okay, so what frequency encoding does, essentially, it's going to take your data frame and the column that you're interested in encoding, and then for every categorical value, or for every unique value in that column, it's going to create a frequency feature. Like it will show you how many times that specific value is occurring in your data frame. So it's a mathematical function. So let me show you how that is done. I'm going to define my function frequency encoder. And it's going to take the arguments of df and call. So what it does, the frequency encoder, let's call it FE, it's going to take my df and then it will group it by the specific column here, which I want to encode. So this column is a categorical value. After grouping it, I'm going to compute the size of the result and then divide it by the overall data frame. So I already have my frequency encoding there. Then I'll just create a new column that's called the original column plus wait for that. Plus. If our column was charts, I'm going to create another column called charts encoded. So basically this is what this line over here does. And what charts encoded does, that is going to take in original column and then map this frequency encoding command that I've passed here. And then once I've done that, I'm just going to return my df. Okay. So to call my function, I'm going to say I'm going to create a different data frame entirely, not this one. So we can say that frequency encoded df is equal to frequency encoder. And the arguments that we'll take will be the new df here. Sorry. And the column of interest, which in our case is charts. So now, if I print out this data frame that we just created, we're going to see that we have a new column here called charts encoded. So instead of now having two new columns, charts 0.0 and charts 1.0, we have just one column called charts encoded. If we want to check out the number of unique values in this new column, which we expect to be 2, we'll do this. Say that dot you can see that we have an array of two values. The first one is 0.93, 1.473, and the other one is 0. That. So that's all about frequency encoding. And just a little explanation. What it has done is that it has taken the number of occurrences of 0 and encoded that as our frequency. So we can say that this category 0.0 occurs 0.93 or 93% of the time, while the other unique value, which is 1, occurs like 6% of the time. So if you add this, you'll get 100%. So basically that's what frequency encoding does. The total of all the frequency encoded values should always sum up to 1. So for some reason, if you get a value greater than 1, then you may want to check your function here and confirm that it's working okay. The advantage of using the frequency encoding over the PD.getDummies or any other categorical, or any other encoding format is that, well, we are not increasing the dimension of our data in any way. We are just increasing one more column for every categorical feature that we have. So if you have 5 different categorical features, then we'll introduce 5 columns. On the other hand, if you're using PD.getDummies, if you have 5 categorical features and each feature has 3 or even more than 3 unique values, then you'll have more than 15 new columns added to a data frame. So basically, instead of increasing the dimensionality, the frequency encoder tries and reduces the dimensionality. That's one advantage. Another advantage is that you may find that maybe you have a train set and a data set, as it happens in many machine learning competitions. And in the trained data set, you have a categorical column, yes, and it has maybe a column like country, for instance. And in your trained data set, you have 3 countries, Kenya, Uganda, and Tanzania. But if you go to your test data set, you only have Kenya and Uganda. So in such situations, if you use the pd.getDummies, on the train set, you'll have 3 columns, Kenya, Uganda, Tanzania, while on the test set, you'll only have Kenya and Uganda. So if you train your model on the train set, you won't be able to apply it on the test data set because the number of columns are not equal. So that's one very big shortcoming of using the pd.getDummies. And to overcome that, I recommend that you get used to this frequency encoder approach. That's all about handling categorical features. Anyone with a question?
Excuse me, sir.
Mhm.
What's the difference between the frequency encoder function you have created
Mhm.
with the value counts function provided by the Python?
There's really not much difference, except that what the frequency encoder does is that it will try and convert the value counts into a frequency of between 0 and 1. Okay.
Yeah,
So
but
rather
even
than, yes.
I think even value count accepts some argument like if you set the normalization to be true, then the values will be between 0 and 1. Can you just clarify?
To be honest, I haven't done that before. I only use value counts when I want to plot the distribution of different categorical features. But maybe you can send me an email showing how you can actually pass other arguments to the value count function.
Okay.
So I'll be waiting. Any other question or concern? Okay, fine. I'm going to move on to the next step, which is finally addressing correlation between columns or features. So Pandas provides us with a very simple way of obtaining the correlation between different features of variables in a data frame. So to do that, you can simply create a correlation matrix by calling that. So now if I call my core matrix, it's showing me the correlation between every individual column in my data frame. And one very obvious observation is that this diagonal over here will always have a correlation value of 1 because it's basically the correlation between one column and the next. So the correlation between crime and crime will be 1, zone and zone will be 1, and so on to the last one over here. Sometimes reading all these numbers here may be discouraging. So Seaborn provides you the functionality of plotting this in a format that is visually appealing. So to do that, it's quite simple. Just passing the heat map argument. It's going to take the matrix as one of the arguments. Then a function of mapping colors. So I'm going to use reds. You can decide to go with blue or whichever color that you prefer. And then I'm going to pass in my title over here. Correlation title, correlation for housing data. And finally, I'm going to show my work. So that's it. So essentially, this graph is essentially this one here, but visualized. You can see that correlation of 1 exists among across this diagonal. And then you have columns which are more correlated to the median, which is our target, compared to others. Now, a few notes about correlation. When working with predictive models, you'll always want to ensure that your features or correlation between features is as minimal as possible. Okay. While correlation between the features, let me repeat what I've just said. When working with predictive models, you'll always want to ensure that correlation between your independent features is as minimal as possible. Like, I don't want my zone to be highly correlated to crime or any other independent variable for that matter. However, correlation between independent features and the dependent feature is usually very encouraged or desired because that will basically show that there is a given type of relationship that can be mapped between the independent features and the dependent feature that you're trying to predict. So in some cases, if you're working with a data that has a lot of features, you may use the correlation heat map or the correlation matrix to try and identify the variables that play a major role in predicting the actual output or the actual target. Like for our case here, I may want to select variables that play a major role in determining the price of my house. And to identify these variables, I may say, okay, I want to select all variables that are that the correlation with the median value is greater than 0.5. And this 0.5 is an absolute value. It can be either positive 0.5 or greater, or negative 0.5 or less, because in the negative axis you move in the other direction. So to do that, I'm going to quickly show you that as we mark the end of today's session. So I'm going to point out that my target absolute value correlation matrix, and specifically want the house price, which is the median value. Now, I want to select that's with correlation values greater than 0.5. So I want all features whose correlation with the target value is greater than 0.5. So to do that, I'm going to say that significant features the core target greater than 0.5. So now if I print out my significant features, this is wrong. If I print out my significant features, target, not core target, we'll see that the number of rooms, I'm not sure what this stands for. But these are the most significant features when it comes to predicting the house price. So this step is very important as far as feature selection for your machine learning algorithms is concerned. So you may want to put this in mind. Now, in conclusion, I haven't gone into details into data cleaning and preprocessing because depending on the kind of problem that you're trying to solve, the preprocessing and the cleaning steps will be different. This is just an example for structured data that is mostly numeric format. Remember that at some point in your career, you may have to interact with text data. Cleaning and preprocessing text data is all